Alright, this is the online version of Lecture 7, Momentum and Collisions. The goal here is that you'll be able to learn what you need to know about momentum and collisions by watching this presentation at home. In addition to this presentation, you're going to take an online reading quiz of Chapter 8. And then when we get to class, we'll be able to have time for momentum and collisions problem solving, as well as reviewing the forces stuff that we really needed to review. So in addition to watching this video and taking good notes, and I hope that while you're watching the video you'll also open Lecture 7 worksheet and follow along with some of the examples we'll cover in this presentation. When the video is done, read sections 8.1 through 8.5 in your textbook and then take an online reading quiz. All of that before class on Wednesday. What we're going to cover in this presentation are the topics of momentum, impulse, conservation of linear momentum, collisions, and center of mass. Momentum can be described simply by its equation. Momentum uses the new variable p, and as you can see, it's a vector, so it has magnitude and direction, and it's easy enough to describe mass times velocity. And if you remember, force has a very similar form. Force was mass times acceleration. So these two equations are similar because, for one, they're both linear, and they are related, and we'll talk about that in a second. Units really quick here. So mass, of course, has units of kilograms. Velocity has units of meters per second. We don't get any special new unit for momentum, so when we have momentum values, the units are just kilograms times meters per second. So, how momentum is related to force? Momentum is the time derivative of force. And as you can imagine, the mass is not the term that's changing with time. So if you plug in the definition of momentum, mass gets pulled out. The thing that's changing with time is the velocity. And so that is how we end up with mass times acceleration for force. So momentum and force are very related. One is the derivative of the other. Something we learned about with forces was the superposition of forces. So that's that funny word that isn't as scary as it sounds. Superposition, all it means is you add things up. So here we have the superposition of momentum. That means that if you have a system of a bunch of particles, each with their own mass and their own velocity, you wanted to know what the momentum of the system is, you could just add up all the individual momentums of each thing. A great example of this would be traffic. So if you're a traffic flow engineer for ODOT, you can figure out what the general flow of traffic is by figuring out what the momentum of the system is. And then you probably need to have M1, M2, and M3 in here to account for the fact that each particle might have its own mass. We are definitely going to see examples today where objects are moving in more than one dimension. So for momentum in 2D or 3D, you need to take into account that the velocity is going to have x, y, and maybe z components. Therefore, you're going to end up with momentum components in the x, y, and z direction. Can't just ignore that because, remember, momentum is a vector. So understanding that it's going to be more helpful when we see examples. Alright, the next concept is impulse. Impulse, we use this symbol J. It's also a vector, and it can be described, this is a simplified form, but it's the one that is probably the one that's going to come up the most often for you, is the sum of forces acting on a system during some time interval. Delta T, of course, can be broken down as T2 minus T1. Okay, so if we look at what the units would be for this, force has units of newtons, time has units of seconds. But if you break down what a newton is a kilogram times meters per second squared, because remember, force is where we get this unit of newtons, and force is mass times acceleration. So if you have kilograms times meters per second squared times seconds, then the seconds on top cancels with one of the seconds on the bottom, and you do have kilograms times meters per second, which was the same units we had for momentum. So these were the units of momentum. But to keep the concepts separate, because impulse isn't momentum, I want you to write impulse with units of newtons times seconds, and I want you to write momentum with units of kilograms times meters per second. So the only reason the book does this is to differentiate impulse from momentum. So if you're given a value, you can see the units and know that they're talking about impulse versus momentum. All right, so let's talk about some scenarios here. If your momentum is constant during some time interval, then your sum of forces, instead of writing force as the time derivative of momentum, you could simply write it as delta P over delta V. Okay, so that's just a simplified version of what we saw before. Simplified. Okay, so if you plug in that definition for force into your impulse equation, now you see delta T on the bottom times delta T on top. And so impulse can also be written as the change in momentum. So that would be P2 minus P1, or P final minus P initial. The mass is not the thing that's changing again, so mass could be pulled out, and you'd have V2 minus V1. So anytime you've got a change in velocity over some time interval, you're going to have impulse. If your velocity is constant during a time interval, then your impulse would go to 0, because then this term equals this term, so that minus that would be 0. Okay, another way you might see the same equation written is just to replace a sum of forces with an average force. Essentially, it's the same thing. Okay, so let's analyze how momentum and kinetic energy might be different. So, just to remind us, momentum is defined as mass times velocity, and kinetic energy was defined last week as 1/2 mv squared. So they're both only relying on mass and velocity, but our kinetic energy term squares the velocity. That's going to make any negative sign on our velocity term disappear, but it means the velocity is going to play a bigger role than mass. So here's an example. Suppose you have a choice between catching a 0.5 kilogram ball moving at 4 meters per second or a 0.1 kilogram ball moving at 20 meters per second. Which will be easier to catch? So from your own life, you might have a sense for what that's like. So think about in your own head, qualitatively, which ball you think would be easier to catch. And then let's analyze it with equations. So how do the momentums of the balls compare? So for, try not to click those buttons while I'm writing. For ball 1, the momentum would be mass 1 times velocity 1, which would be 0.5 kilograms times 4 meters per second. Okay, 0.5 times 4, hopefully you don't have to pull your calculator out, is 2 kilograms times meters per second. Okay, ball number 2, M2V2. The mass here is 0.1 kilogram. The velocity was 20 meters per second. And lo and behold, we still get 2 kilograms meters per second. So as far as momentum's concerned, they have the same momentum. So that doesn't really answer the question about which ball would be easier to catch. If you're curious about how you'd calculate impulse for this example, impulse would be P final minus P initial. So you'd have mass times velocity final minus mass times velocity initial. So we have to presume that once you catch the ball, it goes to rest. So the final velocity would be 0 for both balls. And basically you see that impulse would be defined as the negative of the initial velocity we calculated. So since they both had the same initial velocity, they're both going to have the same impulse. Again, that's not really telling us information about which ball would be easier to catch. Now let's try what happens with kinetic energy. For the first ball, kinetic energy would be 1/2 m1 v1 squared, 1/2 times 0.5 kilograms times 4 meters per second squared. Do that in your head, okay? So 4 squared is 16. You've got 1/2 times 1/2 is basically 1/4. So 1/4 times 16, that's 4 joules. Okay, so that doesn't tell us too much yet. Let's see what happens with ball number 2. 1/2 times 0.1 kilograms times 20 meters per second squared. Okay, you do that, and you should get 20 joules. Alright, so there's where we see a difference. Okay, it takes less energy to catch the heavier, slower ball than it does to catch the faster, smaller ball. And you probably, I'd like to think from your own life experience, guessed that that faster, smaller ball is going to hurt your hand more than the slower, bigger ball. And this is really where you can see it from the physics. The energy required to stop the faster ball is 5 times more than the energy required to stop the slower moving ball. Okay, so hopefully that gives you a little bit of sense of how we can translate these physics concepts to sort of our qualitative understanding of the world. Okay, this walks through everything I just said. Okay, okay, this is a part that's a little different. All right, there's something else I haven't said yet, and that is for a given force that you exert with your hand, it's going to take the same amount of time to stop each ball, but your hand would be thrust back 5 times further catching the smaller ball. So that explains why their impulse values were the same. If you assume it takes the same amount of time to stop each ball, then your impulse calculation tells you, no, actually that's not true. So your impulse equation, J equals force times change in time. In order for their J's to be the same, then the force and the time would have to, by multiplication, be to end up the same value. Okay, yeah, okay, let's just ignore what this said. So not necessarily going to take the same amount of time, but if it takes more time to stop one ball, it's going to, if your T term is bigger, then your force term would have to be smaller. If it takes less time to catch a ball, so this term is smaller, then your force term would be bigger. And that's assuming, like we calculated, that for ball 1, the impulse equals the impulse for ball 2. So in order for that multiplication term to be equal, if one goes up, then the other one would have to go down in equal measure. Okay, so, but we don't have enough information to really answer that. Okay, if you want to try out some of our new equations that we've got for momentum and impulse, you can start working on examples 8.2 and problems 8.12 from the Lecture 7 worksheet. And we'll also hit those when we get to class on Wednesday. So let's talk about conceptual example 8.1. Recall the ice boat race problem we saw from last week. We had 2 ice boats on a frictionless frozen lake. One had mass m and the other mass 2m. The wind exerts the same force on their sails. The boats start from rest and they cross the finish line a distance s away. Which boat crosses the finish line with greater momentum? Now, just to remind you what we did last week we wanted to know which boat crossed the finish line with more kinetic energy. That part was a little tricky until we remembered the work energy theorem. work is equal to the change in kinetic energy, and work was also defined as force dotted with some distance. And so in this case, they both had the same work applied to them, they had the same force applied to their sails, they traveled the same distance, those vectors were pointing in the same direction, so you've got cosine of 0 degrees from the dot product, cosine of 0 is 1, so that just gives you force times the distance traveled. Boat 2 had the same force applied to it, it traveled the same distance. So we found last week that the work of each boat was the same, which means, therefore, the kinetic energies of each boat was the same from the work energy theorem. Alright, this time we want to know which boat has the greater momentum. So if you just look at the momentum equation, mass times velocity, we don't know anything about the velocity. Okay, but this is sort of tricky. Like last week, we had to pull out a new formula to solve for kinetic energy. The work energy theorem, that's our hint, and the hint works this way. We know that impulse equation is also equal to the change in momentum. So if we look at that let's see if I can erase that. Okay, I can't quite easily, so I'm just going to erase that like that. Mass times velocity final minus mass times velocity initial. We assume both boats start from rest, and then they end up with some final velocity, so this term goes to 0 for both boats. So we have that impulse then equals mass times final velocity for both boats. We also have a definition for impulse of force times the change in time. Both boats have the same force acting on them. We don't know too much about time, but we can qualitatively assess this. So last week, we realized that even though both boats had the same kinetic energy when they finished, they certainly wouldn't finish at the same time. The heavier boat is going to take more energy to get it going, so it's going to take longer to cross the finish line, but it would be going faster. So using our logic, we can say that the boat with mass 2m is going to take longer. Higher delta t. Okay, so so J1 would be the lighter boat. Okay, so maybe I'll just call it JM, and then J2M to differentiate the two. They both have the same force acting on them. They have their time that it takes, and what we said over here was that the boat with 2M is going to take a longer amount of time than the other boat. So that means with this number being bigger than this number, the force numbers are the same. Then that means then the impulse of the heavier boat is greater than the impulse of the lighter boat. And we just said impulse is defined as the final momentum. So if their impulses are greater, then their final momentum of the heavier boat is going to be greater than the final momentum of the lighter boat. Okay, you could probably do that if you could figure out a way to calculate an expression for their velocities. You could compare what their final velocities would be and account for the fact that they have different masses. It's possible to do that, actually. And so if you look at the book solution to this conceptual example, it asks you to try that at home to see if you can actually figure out an expression for how these two boats' velocities would differ at the end of the time interval. But here's just a logical way to walk through that. Okay, and looks like I was supposed to do all my work on this page. That's okay. So we did everything on this slide already. Okay. All right. The next concept we're going to talk about is the conservation of linear momentum. Conservation of linear momentum is kind of similar to conservation of energy. So just to remind you, recall, it's me putting my hand on the screen that's doing that. Conservation of energy, which said the total energy at some initial time is equal to the total energy at some final time. And breaking up that into kinetic and potential, you could write that equation as the kinetic and plus potential energies initially have to be equal to the kinetic and potential energies at some final point. Okay, so that's just to remind you, but you can see that form show up in our conservation of linear momentum. So that says that the momentum of a system initially equals the momentum of a system at some later point in time. Now this isn't always true for every single system. This only applies when there's no external forces acting. Then you can have conservation of linear momentum. We're going to analyze collisions, some of which, let's see, I think actually all of our collisions we're going to assume there's conservation of linear momentum. So in real world problems, there may be external forces you have to account for. I think all the problems we do, we're going to assume there's no external forces acting. Okay. So examples, collisions, obviously that's car crashes. A ballistic pendulum is an example we have in Lecture 7 worksheet. That's where you fire a bullet into a wooden block connected to the ceiling by a cord. Just to draw you a quick diagram of what that looks like. There's a block hanging from the ceiling, and if you were to fire a bullet into the block, it's a form of a collision. The bullet gets embedded in the block, and the momentum of the bullet causes the whole thing to swing upward, like that. And during that, there is conservation of linear momentum. Another example is this little desk accessory you may have seen, Newton's cradle, where one ball strikes a series of balls and it launches the very end ball upward. So all that energy gets transferred through these balls. They don't move, but the very last ball gets launched up. So that's conservation of linear momentum and actually conservation of energy right there. And then solid rocket boosters. This is an example of an explosion. So these three examples are collisions. The last one is an example of an explosion. In all cases, there's conservation of linear momentum. Okay, so if you want to try setting up conservation of linear momentum for example 8.6 on your worksheet, you could do that. Just keep in mind that if you're actually plugging in your definition here, for initial momentum, you'd have mass times initial velocity, and then your final momentum is defined as mass times final velocity. Okay, so we're going to, I don't know actually what's coming up next, but let's see. Yes, we can try example 8.5 part A here in the presentation, so you get a sense for how these equations come together. So you have two gliders sliding on a frictionless air track towards each other. Our figure here tells us the velocities, the initial velocities of both gliders, and the masses of both gliders. Okay? After they collide, glider B has a final velocity of 2 meters per second to the right. So notice when it was going to the left, it has a negative velocity, and now when it's going to the right, it doesn't. The thing we aren't given is what is the final velocity of glider A. So VA let's see, V1 and V2. So they're using 1 and 2 for initial and final. So VA2 is what we're looking for. And qualitatively, we know that we should end up with a negative value because we see from the diagram that that cart is going to move to the left. So it should have negative velocity. So we're going to set up conservation of linear momentum. The sum of the momentums initially have to be equal to the sum of the momentums at the end of our scenario. I'm going to make that P1 and P2 so our variables match the figure. And our system includes both carts A and B. So we've got the momentum for cart A, MA, VA1, and the momentum for cart B, MB, VB1. Really wish I could figure out how to erase that. Apologize for that. That's going to equal the momentums of the system, the momentum of the system at the end of the time interval. And notice that we don't really care what happens during the collision. There's stuff that happens during the collision, but conservation of linear momentum says whatever happens before and whatever happens after are related. And stuff happens on the in the in-between, we're not going to worry about it. So this is a nice one-dimensional example, so we don't have to worry about x and y components right now. So for time 2, we have the momentum of cart A and the momentum of cart B. Unfortunately, there's nothing we can set equal to 0, but we're given everything. We have all the masses, we have the velocity initials for both carts, we have the velocity final for cart B. The only thing we don't know is VA2. So at this point, it just becomes an algebra problem. So I'm going to get that term by itself on the left-hand side. Everything else will go on the right-hand side. And then if we divide by mass, then VA2 would be everything on the right-hand side divided by MA. Okay, so you can plug in numbers here. You can verify that you get a negative answer. Okay, you can also do a unit check. So this should be negative. You should get meters per second. We can do a quick unit check over here. So if we see this on top, we have a bunch of momentums added or subtracted on the top. So that would be kilograms times meters per second, all divided by this mass term, which has units of kilograms. Kilograms cancel. We can see we'd end up with units of meters per second. Check. That's what we should get. Okay. As far as what you get here in your answer, I'm sure you guys are capable of typing that into a calculator and getting an answer. Okay. There are 3 kinds of collisions that we're going to learn about. The first is an elastic collision. This is characterized where there's only conservative forces acting, no energy loss due to friction, heat, air drag, etc. So any real-world collision is not an elastic collision. The best example I could give you where a real-world example acts like an elastic collision would be 2 billiard balls that collide together, or the previous example where we had 2 carts on a frictionless air track. They're going to act as about as elastically as possible. But even if you heard a sound during the collision in a real-world problem, you know there's some non-conservative forces acting, but that's pretty minor, the sound you hear. So there will be examples where you have to infer that it's an elastic collision because they say it's frictionless, and that's going to be your key word to figure out whether it's elastic or not. And so in elastic collisions, two things are happening. There's the conservation of linear momentum, and there's a conservation of energy. Remember, conservation of energy required that that there's no non-conservative forces acting, like friction. Now this is similar to the conservation of energy equation, but it's missing all the potential energy stuff we learned. And the reason for that is we're assuming that these collisions happen on a flat surface with just cars or blocks or balls crashing into each other, so no springs and no change in height. And so that basically cancels out the potential energy terms that would have showed up here. But this is basically what we get left from that, from conservation of energy, is that simply the kinetic energy is conserved. Okay, the next kind of collision is basically most other real-world examples, an inelastic collision. You're going to have some energy lost due to non-conservative forces like friction, heat loss, sound, whatever. Mostly friction is your big factor here. So any real-world fender bender is going to be inelastic, or whatever kind of like if you were to roll two soccer balls across the grass and they hit each other, the grass is acting as friction in that example. So in that case, only linear momentum is conserved, not kinetic energy. And then the last case is a completely inelastic collision. This is when you have a collision where the objects collide and stick together. And then they're going to move together as a single unit after the collision. So our ballistic pendulum, where your bullet is fired into a wooden block, and then the wooden block with the bullet inside of it move upward, that's an example of a completely inelastic collision. Or a fender bender where the cars smash together and they stick together, and then both cars slide to some new location after the collision. So that's the wording you're going to look for in a problem where they stick together and move as a single unit, to know that it's a completely inelastic collision. So just like with the regular elastic collision, the only thing that's conserved here is linear momentum. So these two are really similar. Pretty much the only big difference here would be between elastic collisions and completely elastic collisions. So that's pretty much the kinds of problems you're going to see. They're either going to be, there's going to be no friction involved, and so you know it's elastic, or there's going to be something where the objects stick together, and that would be completely inelastic. Okay, so there's some problems on the worksheet where you get to practice this. The first thing you want to try and do is just identify what kind of collision is it. Is it elastic? Is it inelastic? Is it completely inelastic? That's the first step. Okay, so first, and then once you've determined what kind it is, then look at this column, and that will tell you which equations you can use in order to solve whatever it is you need to solve about the problem. Now, if you look here with the elastic collisions, since you're given two relationships here, that means you have more equations to work with. Sometimes that's a good thing, sometimes it's not a good thing. Especially when you're working in 2 dimensions, more equations can mean a longer amount of algebra to solve. Alright, so let's work on at least setting one of these problems up so you get a sense for what you do. On a very muddy football field, 110 kilogram linebacker tackles an 85 kilogram halfback. Immediately before the collision, the linebacker is slipping with a velocity of 8.8 meters per second north. Okay, so he's moving upward, and this is the linebacker, so that's the velocity of the linebacker initial. And the halfback is sliding with a velocity of 7.2 meters per second east. so that's to the right. That's the velocity of the halfback initial. And then it says, what is the velocity, giving your answer in terms of magnitude and direction, at which the two players move together immediately after the collision. Okay, so here's a key word they're telling us. These two guys are going to crash, stick together, and then slide as a single unit to some new location. So they're going to have the same final velocity. And we can see from my drawing here, this is a two-dimensional problem. And we're looking for the magnitude of that final velocity and the angle. Alright, so things that we know. The linebacker's initial velocity is 8.8 meters per second. The halfback's initial velocity is 7.2 meters per second. The mass of the linebacker is 110 kilograms. The mass of the halfback is 85 kilograms. So so collision type, that's the first thing we want to identify. Okay, so they stick together, they move as a unit. That means this is a completely inelastic collision. If you want to go back and reference the last slide to make sure you understand that, please do so. So, I will actually go back. A completely inelastic collision says only linear momentum is conserved. So that's the only equation we get to use. Okay, seems simple enough, but this is a 2D problem. So we've got the x direction and we've got the y direction. In the x direction, we've got the initial momentums in the x direction having to equal the the final momentums in the x direction. And in the y direction, same thing. Okay, and so this term is actually a sum of the two bodies. So we've got the linebacker's initial momentum in the x direction and halfback's initial momentum in the x direction. And then they move together as a unit, so I can just call the final momentum the final momentum. Keep it like that. And the same is true for the y direction. And we can see the subscripts are getting longer, but they do have some meaning. We don't want to just ditch the subscripts. Okay, now we get to fill in our definition for momentum. We have the mass of the linebacker, which isn't going to change, so we don't have any more subscripts on the mass. And then we've got the linebacker's initial velocity in the x direction. And then we've got the mass of the halfback, the halfback's initial velocity in the x direction. And then for final momentum, you've got two guys sticking together. So the total mass would be the sum of each of the guys. And then the velocity is that v final that we wrote over here, but it's in the x direction, so it's v final x. So maybe it would be helpful to draw the x component, v final x. We see that that's adjacent to this angle, so it's going to be equal to the hypotenuse times cosine theta. And along here, we'd have v final y, which is equal to the hypotenuse times sine theta. That just reminds us what v final x equals. And v final y, we're going to have that here in a second. Okay, so I got to fit this size equation into this little space. We'll see if I can do it. So mass of the linebacker, velocity of the linebacker initial in the y direction, plus mass of the halfback, the velocity of the halfback initial in the y direction, equals their two masses added together times v final y. Okay, that's a lot, but things are going to 0. So if you look at our diagram, the linebacker is only moving upward to start. So he only has initial velocity in the y direction. That means the linebacker's initial velocity in the x direction is 0. And that same thing applies to the halfback. He's only moving to the right to start. So he's only got velocity in the x direction, vh initial x. That means vh initial y is 0. So that's good. Okay, so that simplifies our equations down a little bit, and what we're looking for is the final velocity. So we need the x component and the y component. So we can rearrange these equations. The final x would be the mass of the halfback times his initial velocity. And I could ditch the x here, because as I drew my diagram, his initial velocity was 7.2 meters per second. You know that's in the x direction. And then divide all that, thank you for that line there, PowerPoint. Divide that by the total mass of both guys. Okay, and same thing for v final y. It's going to look similar. We've got the mass of the linebacker, the velocity initial of the linebacker, which we can see from a picture, all is in the y direction, divided by the total mass of both guys together. So that's something you can calculate, because we have all the numbers. And then if you wanted to get the magnitude of the final velocity, you need to take the square root of the final velocity, the x component, final velocity squared, and the y component, final velocity squared. It really doesn't like me writing this close to the bottom. And then, of course, the angle would be inverse tangent of v final y over v final x. And now you could have an answer there. So that's how you'd set up this problem. So this was a completely inelastic collision where the only thing that's conserved was linear momentum, but because it was a two-dimensional problem, we have a linear momentum equation for the x direction and a linear momentum equation for the y direction. And it ended up looking kind of long, despite there only being one relationship to deal with. So for elastic collisions, you have both the conservation of linear momentum and the conservation of kinetic energy. So if you saw in the last problem, the 2D problem, we only had to worry about conservation of linear momentum, and we had two equations, x and y. So for an elastic collision, you're going to have 4 equations. A lot of equations equals 4. You've got conservation of linear momentum in the x direction, conservation of linear momentum in the y direction, conservation of kinetic energy in the x direction, conservation of kinetic energy in the y direction. So yeah, that's nice, but it's kind of not nice. That's more like a curse. So one tactic here is that you could write out all 4 equations. You could cross out anything that equals 0, and then identify, of those 4, what's the least number of equations that you might need to actually solve for your unknowns. Try not to use all 4, because at the level of math that you've taken for this class, the tactics you have for solving 4 equations simultaneously are not super helpful. Once you've taken linear algebra, it's much easier to tackle 4 equations at once. But pretty much the most equations you want to try and deal with at one time is 2 equations, but sometimes it can get pretty hairy. So see if you can do a setup at least. For example, 8.12. It should be an elastic collision, so you know that there's 4 equations. At least get them written down to start, even if you're not quite sure what to do at that point. And then that's definitely something we want to work on in class on Wednesday. Alright, so there is a special case of elastic collisions where you don't have to deal with all 4 equations necessarily. And these are one-dimensional elastic collisions. So you could derive this equation if you want. That's a fun little exercise if you want to see where this came from. But this is, I guess you could call it a 5th equation to add to your list. No, actually in a one-dimensional case you would only have the x direction, or y direction. So you'd end up with maybe 3 equations to work with. But as you can see, this equation's pretty straightforward, and usually this will make your life a little bit easier for one-dimensional elastic collision equation. So if you want to try out the usefulness of this equation, you could do the setup for example 810. It's a one-dimensional elastic collision, so you'll have your conservation of momentum, conservation of energy, and then this relationship between the velocities. So let me just check out example 810. So this is the air track example we already saw before, but now we have ideal spring bumpers between the gliders so that the collision is elastic, and so your goal is to find the final velocities of the gliders. Okay, the reason we don't really have to worry about spring potential energy is the collision part of the problem is in between the initial and the final state. So before the 2 gliders are coming towards each other, after the 2 gliders are going away from each other, in those 2 points in time, there's nothing involving the springs being compressed, and that's why we don't have to worry about spring potential energy. So if you look at example 810, you see that cart A has mass of 0.5 kilograms, cart B has mass of 0.3 kilograms. They're initially moving towards each other, going 2 meters per second. Cart B is moving to the left, so it's negative 2 meters per second. And you are not given the final velocity for either cart. So you have 2 unknowns and potentially 3 equations. So you've got the conservation of linear momentum equation, you've got conservation of kinetic energy equation, and then we have this relationship above with the special case formula relating their velocities. And so 3 equations, but you can see this equation is a lot easier to deal with. There's just less terms, the masses aren't involved, so that can be nice if you're choosing which 2 equations to combine. And probably want to avoid your kinetic energy equation if you can, because that squared term sometimes leads to quadratic formulas, and that's just a lot of work, and if we can avoid it, then that's good. So MA VA initial plus MB VB initial equals MA VA final minus MB VB final. Sorry, that's getting really mucked up with those lines there. So nothing goes to 0, but if you use this relationship, so we're looking for VA final and VB final. It's pretty easy to solve this formula for VB final. That would be VA final minus VB initial minus VA initial. And if you plug that up in there, then already you've gotten rid of one of your unknowns. And then you've got VA final, and then VA final would be showing up right in there. And it's a little bit of algebra, but you've reduced your equations quite easily down. So then it's just algebraically manipulating your equation down until you can solve for VA final. You solve for VA final, and then you can plug that back in over here and solve for VB final. Okay, so give that a try on your own. When we get to class, we can go over it and see how you did. Alright, the last topic today seems like it's completely unrelated, and that's center of mass. It shows up in Chapter 8, so I'm going to cover it. Alright, so center of mass, you can write this as the center of mass in the x direction, so xcm. If everything's happening in the x direction, like say you've got traffic flow and you want to know what's the center of mass of all the cars, then that would be described with just an x variable. The subscript cm tells you it's talking about the center of mass. Things to be happening in the y direction, you know. If you have something, a system of particles that are all moving in 2 dimensions, then locating the center of mass might require a vector that would start on the origin and point to the center of mass in that 2-dimensional field. So that's another option too. We're talking about a distance from some origin, and so the units, of course, would be meters. So center of mass can be used to describe the center of a single body. There's a very complicated formula to determine where the center of mass of a human is, for example. Or it could be the example with cars or something, the center of mass of a bunch of objects that are all moving through an area. So for this simple example we see up in our figure, we have 2 objects on an XY plane. They're not necessarily moving, they're just sitting there. But if you wanted to know the center of mass between those 2 objects, this is the formula you would use to do that. So you have the mass of 1 times its position, the mass of 2 times its position, divided by the total mass, m tote. We're going to see m tote on the next page. I think it becomes capital M. So if you're talking about something in 2 dimensions, let's say you've got objects all throughout this 2-dimensional space. Let's say you're bored at a party and you're interested in figuring out, for all the people standing in a room, what's the center of mass for all those people. So you can imagine these are all the people standing around in a room, and you want to figure out what's the center of mass of all of them. And so you could figure that out by sort of breaking it up into x and y components. So everybody's going to have a position along the x-axis. So let's see, this is body 1, 2, 3, 4, 5, 6. So each one's going to have a position along the x-axis, x1, x2, x3, so on and so forth. And you could figure out what the center of mass along the x-axis is with this equation just by adding up all the mass times positions and then dividing by total mass. This is m1 plus m2 plus blah plus. Alright, so that you see when you write it in terms of this summation, then you get capital M to describe total mass. Okay, and then same thing for the y direction. All of these objects are going to have some coordinate along the y-axis. y3, y1, y2, y4, y5, y6. Okay, so you could figure out what the location of the center of mass in the y direction is as well. And then that would lead to basically this formula to describe some ultimate location. So if in the x direction the center of mass of all these bodies ends up being right here, xcm, and in the y direction the center of mass for all these bodies ends up being I'm going to exaggerate because I'm running out of room. Let's say this is your YCM. So you draw how those two components would come together, and you have your vector then. That's your vector RCM. Right? So it's got an X component and a Y component, and that R vector itself has some magnitude, and you can see it's got some angle you could calculate. For simple objects that are symmetrical and uniformly dense, the center of mass is just the center, the geometric center of that object. So a cube, a sphere, a cylinder, that makes total sense, or a disk. The center of mass will always lie along the axis of symmetry. So we see the axis of symmetry for all these objects. You know that you can see that the center of mass lies along the axis of symmetry. And then for the donut, that's a little tricky because we see the center of mass is the very center of the donut hole. There's actually no mass located there. That's just the center of mass. It doesn't mean there actually has to be mass there. Alright, now you could have objects in motion and try and figure out what the center of mass of all those moving objects are. Again, think that traffic engineer that works for ODOT. So the velocity of the center of mass is simply the derivative of your position center of mass that you just calculated. So your equation looks really similar, just that everything that was an x term before now becomes a velocity term. And again, you can pull out the total mass, and then look at that. The top of that equation up there, mass times velocity 1, mass times velocity 2. Those are all momentums, right? So you could write that as 1 over the total mass times the momentum of object 1 plus, I guess in the x direction, right? So we wouldn't have a vector symbol, plus the momentum of object 2 in the x direction, so on and so forth. So what we see then is in this line here, they've moved the center of mass to the left-hand side. So you've got, or excuse me, the total mass. Total mass times the velocity of the center of mass gives you the total momentum for the system. So this is sort of a sum of all the momentums in the x direction. Sum of all momentums in x direction. And that's why it's a capital P instead of a lowercase p. I don't know why the book doesn't call it P total or use the summation symbol, but they don't. So that gives you another formula here, where you've got total mass and then the sum of all the momentums. So again, this is the x direction, this version is the y direction. So for a system of particles with no external forces, the total momentum is constant, because that was our rule for conservation of linear momentum. That's from Conservation of Linear Momentum. So if your total momentum is constant, as in mass times the velocity of the system, then the velocity of the center of mass of that system is actually constant. So you think about traffic flow, you've got individual cars speeding up or slowing down, but you can see the net effect of all those cars moving as a unit, then their velocity is going to be constant for certain periods of time. Okay, so Lecture 7, worksheet problem 8.4 will give you the chance to practice some of these center of mass and center of velocity calculations, and that's again something we can go over in class if you weren't quite sure how to answer that. Okay, so that covers the content of the lecture. Your next step is to read sections 8.1 through 8.5 in your textbook. This is speed reading, so don't get bogged down in the details. You're going to be looking for key definitions, try and understand figures. The formulas should be familiar now that you've seen this PowerPoint. And then once you've done that, you're going to take the online reading quiz. And when you get to class on Wednesday, We'll go through all the problems that I referenced here in this PowerPoint, and we'll also be reviewing forces and the concepts from Lecture 6, that's work, energy, and power. We'll review the reading quiz to make sure that you understood what you should have read, and then we'll be doing Lab 4. And that's going to keep us busy, so don't make any plans to get skipping out of town before the normal time, because as much as I'd like to do that too, we have enough stuff to do on Wednesday, and we won't be able to get out of there early, probably. So, thank you for watching, and I'll see you guys on Wednesday.